Looking for. Oh, sorry.
Sorry, are we, is this, oh, it is recording. Okay, cool.
Yeah, it's already recording. Yeah.
Okay, cool. Sorry.
No worries.
Just so I didn't get like half an hour in and you're like, by the way.
Well, it's their best effort anyway.
Like I know in the
Okay.
US, like the first 2 years of it, so you're basically the masters.
Yeah, so most.
Okay, and Stefan's not coming, right?
I don't think so.
Okay, cool.
It's also best effort.
Perfect.
They have a direct entry.
Okay, so I guess it's about 10 past and the room filled out substantially in the last 5 minutes. So hi everybody, I'm Katie or Katharine, whichever you prefer. I'm a postdoc at Ghent University, where most of my research focuses on automatic differentiation and GPU acceleration for tensor network methods. I've been using Julia since 2015. So my Julia career is almost old enough to browse neopets.com on its own. If anybody's old enough to have ever used Neopets. So today we're going to be going through some basics of implementing a state vector simulator in Julia. It's kind of a continuation of what Ray was talking about yesterday. So sort of going from zero to hero, from really basic stuff to stuff that's a little bit more advanced. So I'm going to share quickly. Perfect. Just some setup instructions. So before we really get rolling, people in the back, is this legible to you?
Yes. Can you just get rid of the meeting info?
Yes. Is that better?
Yep.
Cool. Okay. So we're going to be doing all the material for the course today in a Pluto notebook. So quick show of hands, who here has used Pluto before? Okay, like 3 people. Perfect. Who here has used a Jupyter notebook before? Okay, most of the room. Perfect. So Pluto is kind of like a more lightweight version of a Jupyter notebook because Pluto is a dwarf planet, so it's really small compared to Jupyter, which is really big. So it's a Julia sort of stateless notebook, and there's sort of 2 ways you can interact with it today, and also we're going to be using it for other courses, so if you get this set up now, you'll have a much easier time for Lucas's lectures in the morning. So you can either install the Pluto package yourself on your machine, or if you don't want to do that, you can run everything in the browser. Like, for example, if your laptop isn't super strong, or you are, I don't know, like playing Cyberpunk instead of doing the notebook on your laptop, you want to run it in the browser. So here are some quick instructions. If you want to get it set up, you can start your Julia REPL as we did yesterday. You don't need to activate any specific environment. Just enter package mode, add Pluto, and then you can close and restart the REPL. Or you can go to the website plutojl.org. Hold on. Am I allowed to go to new tabs in my own? Yes. So if you go to pluto.jl, there's a try online button, and you can try Pluto online and yeah, I'll hit that, although I actually am going to be using it locally. And then if you're in the Zulip chat, I will paste some links, which actually I just sent. So the first one is the repository that contains the Pluto notebook we're going to be running today. So you can paste the URL of the notebook into this whenever it actually finishes loading. Oh, I scrolled away, so that's why I did that. Or you can paste it into your Pluto window when it starts. So any second here.
Did you also show the thing again that showed how to install it?
Yes. I will go back here. So I'll leave this up for a little bit while I set my copy.
Yeah, this is
I think so, but I usually don't use VS Code. So if you want to give it a spin, I'm sure it will work well. I'm just a VS Code hater because I hate Microsoft. Sorry, this is being recorded. Also, if you're having trouble with any of the steps, just please put up your hand and somebody who has used Pluto can probably help you.
Do it on my VS Code terminal, that's okay.
Yeah, that's also fine. So in whichever way you're using, I'll show the REPL steps in one sec, but what you should end up with is something that looks like this in your browser. And then you can use the URL of the repo I pasted in Zulip to get to the notebook. So I'll also paste the exact notebook URL in 1 second. Oh my God.
If we're using it locally, should we clone?
You don't have to actually. So if you're going to use it locally, it says open a notebook, enter path or URL. So you can also just enter the URL in there. So if you're using the REPL, just give me 1 sec. I'm having to like manage sharing multiple windows here. How do I pick which window to share? Okay. So for those REPL heads, is this readable? Once you've installed it, you want to just run import Pluto, semicolon, pluto.run. So I'll kick that off here. Oh, it might yell at me because I already have one going. And then you can just go back to your browser and you should have the sort of landing page for Pluto.
So the site didn't pop up after I downloaded it. But
Are you doing it in VS Code or the REPL? Did you in VS Code launch the Pluto server?
Or maybe I didn't launch it.
Yeah, that could possibly be why.
I'm sorry. Relaunch. Yeah.
Yeah, sorry.
Thanks.
Okay, so if you've reached this screen, you're good. Nice. Thank you, Lucas. Yeah, really quick. Yeah, sorry. It's really annoying because I can't like split my share. I'll also just paste this into Zulip for people who are using the REPL. Just give me 1 sec.
And then there's some.
Okay.
I did not know.
I had to.
Oh, hey, what's up?
So I did open the browser and wait, but did you say something about Zulip? Something?
Yeah, so the URL of the notebook is in Zulip. So yes. It's statevector.jl. The URL that ends with that. Hopefully this opens for me. Blob. Okay. So quick show of hands, who has the Pluto stuff more or less set up at this point? Most? Okay. Is anybody still completely stuck? Okay. One more there. Oh, two. Okay, we got two. Yeah, put up your hands again, sorry.
Did you restart?
Okay. And folks have this open, more or less. Okay, so the way Pluto works is unlike Jupyter, where you can run the cells in any order, the entire notebook only runs if every single cell is able to run in the chronological order. So one thing that's nice about this is you can't have a situation where you manage to change what something in a cell in the past is doing by running a cell later down. So either the entire notebook executes in one go or it doesn't. This can be like kind of annoying, for example, if you're making a bunch of calls to a remote HTTP service, but for just like running a tutorial, it's really nice. The other thing that's kind of nice about it is it starts in safe preview mode. So it doesn't actually run any code when you start it up. So you can see there's a, maybe you can't see actually because of the way the border is set up, but there's a big blue border around my screen and probably yours. And that's saying that this is in preview mode, it actually hasn't run anything yet. So that lets you, if you wanted to, you could go through the whole notebook and see what is in here so that like I didn't include some sort of Bitcoin miner in the Pluto notebook to hijack your machine. I didn't do that, but just in case. Well, and then, once we're ready, we can start running the notebook code. It's going to ask if I trust my own file. I edited this late at night yesterday, but I guess I trust it. So this will start compiling and running every single cell in here, and then we can start actually going through the material. Anybody got questions so far? Okay. So today we're going to be sort of continuing what Ray was talking about yesterday, doing some basic state vector simulation. So also just another quick poll. Who here would say that their main background is in physics? Most people. Who here would say their main background is in CS? Okay, actually quite a few. How many people would say their main background is in math? Okay, there's a couple. There's somebody back there who's like not putting their hand up very high. You don't have to be embarrassed. You're welcome.
What about engineers?
Well, I was gonna get there. Sorry, I was making fun of someone for not putting their hand up. Yeah, and then how many people would say their background is more in engineering? Like ECE? Like what kind of engineering? Okay. Maybe this is like a hot take, I guess, but I would put you guys almost as in like the wider CS group. At least for our purposes.
Chemistry?
Oh yeah, chemistry. I'm sorry, I completely forgot about chemistry. Okay, and who here would also say their background is in chemistry? I can't put up my hand, but all right. So we have a pretty good mix. So unfortunately, most of you are completely surrounded by physicists. But the good news is, if you get confused about some of the material in this, you can probably turn to your neighbor and be like, "What is this?" So I'm gonna volunteer all the physics people to help out anybody who doesn't know what a qubit is or a two-level system. So we're gonna remind ourselves of some basic facts about state vectors, or remind ourselves for the first time, maybe. So we're gonna claim that a state vector is a length d to the n complex vector, and it represents probability amplitudes for some quantum system of n particles, with each particle having d possible states. So already I've made a bunch of assumptions here, like all of the particles are basically identical, but okay. We're just going to keep rolling with the simplified assumption for now, and we can discuss how to complexify it later. So for qubits, which is by far the most common thing we're going to simulate, because, for example, we might want to simulate a quantum circuit, we say that they have two possible states. That's where the B comes from for bit or binary. And we helpfully label these 0 and 1. And then, because there's only two possible states, the state vector describing a system of n qubits has 2 to the n elements, whereas for another system, for like q trits, which have 3 possible states, it would be 3 to the n, and for q dits, which have d, it would be, again, d to the n. So since we want to represent this quantum system on a classical computer that does deal in binary arithmetic, the q-bit case is by far the simplest, and that's the one we're going to focus on now. But it's worth remembering you can extend a lot of this logic for systems that actually have more possible quantum states. So if we just had a single qubit, like a single quantum particle that has two possible states in its eigenbasis, 0 and 1, we can write that as a two-element vector. So there's psi0 and psi1. These are both complex numbers. Or we can write it in this Dirac notation as a linear combination of the eigenvectors 0 and 1. And then again, these scalars here, psi0 and psi1, are just scalar complex numbers. So we would probably want to force that this state is normalized so that psi0 squared plus psi1 squared is equal to 1. And then if we wanted to keep extending this and say, okay, now we are going to have two qubits in the system, we want to represent the state vector of both of them, we would have a length 4 vector that just has 4 complex numbers. So 0, 1, 2, 3. So one very frustrating thing that we're going to encounter over and over again in this lecture is that Julia arrays are 1 indexed. So if the first element of the array is 1, and for a variety of historical reasons, in quantum mechanics, we usually label the first state as 0. So we're probably going to, well, maybe you won't, but I will be making probably a bunch of op by 1 errors for the entire lecture. So we can also ask ourselves, what do these like 0, 1, 2, 3 actually correspond to? So 0 is the coefficient of 0, 0. 3 is the coefficient of 1, 1. And we actually have some freedom here in terms of which of psi1 and psi2 we attach to the other states 0, 1, and 1, 0. So again, in this case, I'm going to say that 1 corresponds to 0, 1, and 2 corresponds to 1, 0. But this is effectively a choice I've made. And for the computer science people, you might have encountered this before in terms of representing integers on classical hardware, where people sometimes call this endianness. So from which end of a byte you start counting 1 versus like 64. This also is a super common cause of extreme arithmetic errors. There's a CS person, or sorry, ECE person in the back there being like, oh my God. So it's just worth remembering that we have to make a choice here, and now that we've made it, we should be consistent about it. And you can also say, well, like, Katharine, this choice is garbage and I hate it, which is also completely valid. So you could make the other choice and instead say that 1 is 1, 0 and 2 is 0, 1. You just got to keep consistent and remember which one you did. The risk comes from being inconsistent. And I already kind of alluded to this, but we can then start combining these smaller, like 1 or 2 qubit state vectors to make larger ones. So if you study quantum computation, I mean, it's fun to look at systems of small numbers of qubits, but of course, what people want to actually do is use much larger systems to simulate various either physical systems or solve things like the 90 billion hidden subgroup problem. So we can combine smaller state vectors into larger ones through this Kronecker operation. And usually we do this in a way, for the ease of writing stuff by hand. When a lot of this was developed, we don't actually include the Kronecker operator between the various elements of psi here. So really this 0, 0, 0 is 0 on qubit 0, Kronecker, 0 on qubit 1, Kronecker, 0 on qubit 2. But again, for ease of writing or me having to write the LaTeX for the Kronecker-product, we usually just write it in a compressed format like the above. Okay. Going to take another sip of coffee. So we have a bunch of state vectors that represent some qubits, and the qubits are in some particular state. But now if we want to actually simulate the operation of some quantum device, like a quantum computer, we need to be able to apply some gates to those qubits, and then we can actually simulate us performing some computation. So a quick aside here is that for the initial part of this, we're going to only focus on state vectors, which represent what we call pure states. So we're going to avoid considering noise for now, and worrying about mixed states and density matrices. We'll come back to that later. Hopefully we have time to look at it in more depth in the afternoon. But for now, we're going to pretend that the quantum computer has like perfect fault tolerance. There's no noise. Everything's super chill. And then we'll be able to add in sort of the more realistic complexity later. And the other thing that's going to be nice is what we develop here for the state vectors can actually be repurposed for the noisy case pretty easily. So if we're going to apply gates to these state vectors, we should actually think about what it is we're really doing. So these gates represent analogs of these classical logic gates, such as NAND, OR, AND. Again, the folks in the ECE CS side probably pretty familiar with this. If you're coming from a more physics background, this might be a little new. And later this week, i.e. this evening, we're going to talk about simulations with a subset of gates that are called Clifford gates, which can be done extremely efficiently. So stay tuned for that when Stefan covers it later. But here we consider a generic panoply of quantum gates. So we can say that a gate is some m-qubit unitary operator that can operate on anywhere between 1 and the total number of qubits in the system. And for our purposes, that means we can represent every single qubit as a matrix of complex numbers, and it's of size 2 to the m by 2 to the m. Okay. So there are a lot of gates that people have developed. Probably some that people are relatively familiar with are X, Y, and Z. Sorry, I'm Canadian, so I always say Z. So I guess go Team Commonwealth, who also say Z. If you say Z, you can just leave now because you're... And others, the Hadamard gate, rotations, RX, RY, RZ. See, I did it again. And then some of the entangling gates like controlled X, double controlled X, swap, and then 2-qubit rotations. But there's plenty more. The IBM Qiskit SDK has a really nice list of all of the various gates that people want to simulate, some of which are more suited to various hardware platforms than others. So we're going to try and write some gate application code that's like relatively generic, and then that should let us actually apply these various gates in a reasonably efficient way without having to write a huge amount of code. So since any of these gates is a unitary operator, we can apply it as we maybe learned in Quantum 101 if we ever took that class. So we apply some unitary U to an input state psi, and then out comes some state phi. And my LaTeX didn't render correctly for U. This is really frustrating. For psi, I'm sorry about that. So if U is an operator on the same number of qubits that are spanned by psi, this is like pretty simple. It's just a matrix vector multiplication. Hopefully we all remember vaguely how to do matrix vector multiplication. But then we kind of run into a slight issue if we're applying something like a single qubit gate to a state vector that's covering, let's say, 2 qubits, as I've shown here. So imagine that you have some input state psi, which is just this vector, and you want to apply x only on qubit 1. So here, what you would actually in practice, of course, be doing is applying the identity on 0 and then Kronecker with x on 1. And this way you have the correct size of matrix to apply to psi. Okay, so we can write some code to do this. So I have some examples here. First, we can write down the matrix representation of these simple gates. And we're going to focus on the ones that don't have angles or parameters in them just for simplicity, although we can add that in later. So we'll go through the poly basis, X, Y, Z, and I, and then we'll add in the Hadamard as well. And one thing that's also kind of nice about Pluto is if you have these single lines, it'll display this kind of the result above the line, but every single cell of code in Pluto has to be either one line or one block. So you can't get this situation you get in Jupiter where you have like sort of this massive output of many functions being applied in one cell. And then I've written here this very simple naive gate applicator. So again, as Ray was showing yesterday in Julia, you can use Unicode symbols for variable names. So I named my input state vector psi. We have some gate coming in that's just a matrix. Here I've used some type annotations to say like, okay, you know, the psi had better be some kind of vector and the gate had better be some kind of matrix. And then I include also whichever qubit the gate is going to be applied to. So this is applying just a single qubit gate to some arbitrary psi that could span many qubits. So here we figure out what number of qubits psi actually spans using this beautiful computation here. And then we form the number of identities. So the I here is just Julia's way of representing the identity matrix. We sub in the gate we want. And then we can actually use this reduce operator to apply the Kronecker-product to all of the gates on every qubit. And so we generate a 2 to the n by 2 to the n matrix where n is the number of qubits in the system. And we can just multiply that by psi. Okay. So this is sort of the most naive way to set up some quantum circuit simulator. And it only works right now for single qubits, although we'll discuss how to extend it to more later. So we just construct the full matrix for the entire unitary operating on the system and multiply it by psi. And so we can just quickly test that this works. So we can write out by hand for a simple 2-qubit system what the result of applying x to this input state is. Remembering that we're applying x to qubit 1, so we're going to flip qubit 1 here. So psi 0 now matches 0, 1, and psi 3 matches 1, 0, because we said that the 1th qubit, or the first qubit, is the one to the right. And so then you can actually just check the result of applying this to your function if you put it into my apply gate naive. And you see that, in fact, you get the correct result if you work it out by hand. Okay. Yes.
Does Pluto have the ability to take your code and write it into like hand script? You know, you did it manually here.
I don't know, actually. So like all of these like LaTeX blocks are just marked down, like in Jupyter. And I wrote those all out by hand, but I don't know. Actually, do you use Literate at all?
So
Yeah.
I think in this case, you can actually open the file and like open it in VS Code or whatever you like and run the things manually line by line. Because I don't think, I mean, you're running everything sequentially.
Yeah.
So it is just like a Julia file script, and you will see that there's like a bunch of like commented annotations in there, but it should, well, it might just work. Let's say it like that. So if you just open the .jl file in any editor, you can use it as normal.
Although it's a little, you have to be careful with this because like in the Pluto notebook, it has some comments saying like, here's all the packages this notebook needs. And so if you just want to run it as a regular .jl, you'll need a project.toml saying like, hey, here's all my depth. And also like when I created this, I was using a slightly older version of some of the packages, and Pluto also keeps, it has effectively like a manifest embedded in the file saying like, hey, you ran this with, I don't know, like linear algebra 1.11 last time. Do you want to update to the new one? So if you want to run it just as like a regular handwritten file, yeah, you just have to do the package management yourself. Sorry, my chair is like about to fall from under me. What's up?
Yeah, are psi 0 and psi 3 just like 1 over root 2 in this case?
Yeah.
Okay.
Yeah. So here I came up with sort of like a example state, which is actually just some bell pair between 0, 0 and 1, 1. And I kind of implicitly enforced that it's normalized. And then I put that in to my naive gate applicator function and just checked that it is indeed matching what comes out if I work this out by hand. So of course, this doesn't protect you if both your function and your result working it out by hand are wrong, but it's at least like an attempt. Okay. Oh yeah, go ahead. Sorry.
So Krone, I guess, in the function you wrote, that's like a native Julia.
It's in the linear algebra standard library. So linear algebra ships with Julia, but you have to explicitly import it because I mean, as Ray again was saying yesterday, like Julia kind of grew out of a bunch of linear algebra tooling, but for whatever strange and deranged reason, some people want to use the language without using a bunch of linear algebra functionality. I don't know why you would do that, but people apparently do. So you can choose whether or not to load in the linear algebra stuff. And there's a bunch of other, like the sparse arrays is also its own standard library that you can pull in or not. Like if you don't need sparse functionality, you probably don't want all of this. And there's a bunch of other STD libs like that. But yeah, cron is available in linear algebra, and it just implements the Kronecker-product for you. Okay. Other questions before we go to multi-qubit gates? So I wrote this very naive function for a single qubit gate. Now we can look at something that's a little bit more complex. And in this case, we're going to look at this famous gate swap. So this, as you might guess from the name, swaps the state between two target qubits. So I've written a quick example here where, again, my LaTeX didn't render correctly, which is probably my fault. Sorry about that, R angle. So I have some state here, psi 2, which just has, you know, it's some linear combination again over the 4 possible states on 2 qubits. And swap, wow, okay, the LaTeX here really came out badly. We'll just exchange the psi 1 and psi 2 between 1, 0 and 0, 1, but it leaves psi 0 and psi 3 untouched. So this is effectively an entangling gate. And you can also see if I actually read out its sort of full matrix representation here, you can see that, yeah, this is not diagonal and it mixes these two channels 1, 0 and 0, 1. And so one interesting thing about this, I guess, is you can ask yourself, is it possible to write swap as a Kronecker-product of two single qubit gates? I'm kind of giving the game away here with like Betteridge's law of headlines. So one exercise that you can do is try and apply this apply gate naive function up here with swap. So how would you change this function to now take two input qubits rather than just one? And for now, you can assume they're adjacent since this makes life a lot easier for you. So I think maybe it makes sense, like we can spend a few minutes thinking about this and then move on. And I'll release after today an updated notebook with worked examples, which you can look at or not look at your leisure. So if you want to try, like, how would you modify this naive gate function for the next like 5 minutes or so, or grab a glass of water if you don't want to do that, or just like hang out with your buddies, and then we'll keep going. And then again, I'll release a version of the notebook with the solutions that you can check later if you get stuck and want a hint. Or you can just ask questions during the next 5 minutes too. Oh, yeah.
I'm just having like a little problem on mine. Could I?
Oops, sorry, Lucas.
It's good timing though. We're having a break right now. Sorry, so I don't know if that's what you guys were doing.
This is exactly what I was talking about. I also I have no idea. It's also that I get no diagnostics, like it seems like your computer's entering like it has to.
Because if I try to rerun it, just like gets to here and then.
So like one of the ways you can follow along with fixing the issue is to It's been unfortunate, but very smart.
I'm gonna try and fix my LaTeX.
Would this try online?
That should work.
I'm trying to do it through there.
There we go.
Maybe you can use.
I wonder if it's related to somebody else to something.
Is it out of memory?
Can we just have the vector of indices and then
Are they running them in the browser or on their machine?
and modify
Oh shoot! What browser are you using?
Oh, by multiple.
Yeah, do you have Firefox? Do you want to try that? I usually am a Firefox head, and it worked for me last night. But okay, it works for me in Safari, but I think it's crossed.
But if not, it doesn't make
What's up?
This might be a silly question because I might not understand the Kronecker operation good enough. But in the original function, in the all gates term, it seems that the order is reversed, right? So if you want to apply on qubit gate 0 or like on qubit 0, then it's the last one on that list that becomes that gate, and so on and so on. Why is it that the order is reversed in the all gates list? I'm not sure I understand that.
Oh, yeah, so this is going back again to this issue we mentioned above about the endianness. Where did I put this? Where we're counting like this qubit here. Can you see my, yes, okay, that's qubit 0 and this is 1. And then when I want to apply this here, yeah. Oh, it's also because of the one indexing, I think.
Yeah.
Like if the gate qubit is 0, like if I'm applying this to qubit 0, if I insert this as 0 or wow, I got scrambled there for a second. If this one is 1 and the number of qubits is 2, then I want to apply to qubit 1. If I'm explaining that way. Yeah, it's also, yes, indeed, that the cron is flipped. I probably should have used fold L there, but oh well. Yeah, cron. Yeah, BA. Okay, cool. Oh, and we made it 5 minutes. Okay. Are people good to keep going, or you want another like minute or two? No response.
Is there a way to test?
Sorry?
Is there a way to test it out, like when you write it down?
Yeah, so I mean, one thing you can do is like, for example, I have this sort of example up here with 2 qubits that shows what should happen. And so you can just write some hand-tuned cases and just check.
Oh, I see.
Like that's what we did up here also with the apply gate naive. Okay, we'll give people another maybe 30 seconds and then we'll keep rolling. Okay. So in the interest of time, because as you can see, we're like not very far into this notebook, I'm going to keep moving to the computing expectation values. But if you want to keep working on this separately or on your own, go crazy with it. And again, I'll post a solution notebook later. So in addition to applying gates, if we want to simulate the operation of some quantum computer, we need to be able to compute expectation values. Since that's actually sort of effectively what we're doing when we're making a measurement and looking at the output of some permission operator, i.e. an observable. So in Dirac notation, we would write this as the expectation value bracket operator for some arbitrary Hermitian observable O. This is effectively an inner product, and one way you could implement it would be to first just compute the effect of O on the one side of this, and then compute the inner product between that and the original vector. Although, in fact, Julia helps us out because it has a dot function that can compute this top-level object in one fell swoop, which is really helpful. And it will also handle complex numbers correctly, which is another very common source of bugs when computing inner products. So here I, again, pull in the linear algebra operator. And then I can write a function that's really similar to the gate application naive method, but now for computing some expectation value. Sorry, Lucas. Where I have some observable O that I want to measure, some qubit that I want to measure it on. So again, I'm just going to look at the single qubit case here, and then some state vector psi that I want to measure it with respect to. And again, I just compute the number of qubits, form the full matrix that represents O, and then finally compute the dot between psi and full O. So again, for this function, I can go through and just check that I get the right answer. So I worked out by hand with my beautiful parentheses here what the correct answer should be. And at least this looks correct. And you can also check if you want that it's correct for single qubit operators like X and Y. So what we're effectively doing here, especially if you apply more than one gate after another, is you're constructing the entire unitary for the whole system for every single gate. And then if you do that repeatedly, you're effectively computing one very large 2 to the m by 2 to the m unitary and applying it to a state vector. So this is relatively simple to implement, but there are a lot of drawbacks for it. So some pretty obvious problems here are that we were looking initially at really small systems like 1, 2, 3 qubit state vectors, but the size of this unitary is going to scale as 2 to the n by 2 to the n. So you can imagine if the number of qubits in the system becomes large, where large is like 30, this is going to become completely infeasible because 2 to the 30 by 2 to the 30 is too big to fit on anybody's laptop. And the matrix vector multiplication is going to be just extremely expensive because both objects are very large. The other reason this is maybe not the best idea is that most of the quantum gates we're looking at are local, so they only apply on a few qubits, usually 3 or fewer. There are some exceptions to this, but generally this is the case, partly because for experimental reasons, implementing gates on large numbers of qubits is really hard. And again, this is especially true for superconducting systems. So if we're taking these repeated outer products to construct a unitary over all of the qubits, we're effectively wasting a huge amount of compute on just like totally spurious calculations, where we're just doing the Kronecker of the identity matrix with itself over and over again. And also, if you have gates that span more than 1 qubit, like swap or whatever, and you want to handle 2 qubits that are not adjacent to each other or not contiguous, and you can't decompose the gate into a Kronecker-product of 2 single qubit gates, this is kind of substantially more irritating to have to set up. But for really small systems, this technique can actually still do very well. Like by really small, I mean like 8 qubits or fewer. And it's also useful for testing purposes because it's quite easy to set up and determine if you did something crazy. So now we can look at how we could do this with a slightly less naive approach. So if we go back to our 2 qubit state vector psi2, where I've again just written it out like this with its 4 complex scalars, we note that we could easily reshape this into a 2 by 2 matrix so that each dimension is corresponding to a single qubit. So if I just reshape this thing, then I can see that the column index corresponds to this first qubit here, and the row index corresponds to this qubit here. So is that reasonably clear to people? You can stare at it for a second if it's not super obvious. And if you had 3 qubits, i.e. a state vector with 8 elements, you could then reshape this into a 2 by 2 by 2 or a 2 by 4 or 4 by 2 object. So what's nice about this is if we're a little bit careful about how we do the reshaping, we can apply gates without having to perform a huge number of these outer products. So this is often called like a reshape, permute, gem, and then reshape approach. And we need to think now a little bit carefully about how the Julia arrays are actually stored in memory. So Julia arrays are stored in this so-called column major order, which means if we have a matrix like this, in the actual memory encoding, the first element is this one, and then here and here. This is also why I secretly chose to represent the matrix this way. But it means if we're not careful about which dimensions we reshape and permute, we'll get the wrong answer. Okay, so I created a goofy 3 qubit state vector here, which is not normalized. It's just for demonstration purposes. And then we can look at the so-called linear index of this thing, and just see like which element is actually stored at which position in memory. Since this thing is a vector, it kind of makes sense that since it has linear ordering, if I just print out the index and then the value that corresponds to it, at index 1, we have 1 or 0.1, and then the second item here. Seems reasonably simple. And then if I start reshaping this vector into various, different shapes, so either a 3 tensor or 4x2 or 2x4, you can see how either the first or second dimension, is represented, but underneath the hood with this linear indexing, the underlying memory layout is still the same. So we can use this to apply the gates we wanted to look at in a far more efficient way. So if we wanted to apply X to some qubits, we can again, just for safety, work out by hand what the result would be. This state vector is long enough, you might have to, like if you're like me, you might have to scroll a little bit to get the fully worked example. But I just worked out here what the result has to be for applying X to qubits 0, 1, and 2. And then so, for example here, another LaTeX error. I've created a function apply gate reshape 1. So this is sort of like a first guess for how we could use this. We have the input state vector psi, the gate, and then the gate qubit it's applied to. Again, we're just going to focus on the single qubit gate for now. And here I just reshape it to a 4x2, and then reshape at the end back to a vector after just doing a matrix multiplication. So here I've also again implicitly assumed that this matrix is 2x2. Yeah.
When you reshaped it like in 2, 2, 2.
Mhm.
And then you reshape the same thing with 4 and 2.
Yeah.
Like computational wise, like which one will be more?
Do you mean of the reshapings or?
Like you're adding a dimension more like things is going like that.
Yeah.
I mean, you're adding the rank, but the dimension is going down. Like which one will be more efficient? Like having more higher rank of the tensor with lower dimension.
So here at least, it actually shouldn't make a difference because it's just going to pass the underlying pointer here to BLAS. And just say like the stride on the dimension you're not contracting is whatever it is. But later on, it does make a difference, and we'll probably cover this. Yeah. I mean, so these reshaping operations, like this is effectively just putting a mask on top of the array. It doesn't actually do any work, if you like. It just says like the indexing semantics are slightly different. Yeah. Yes.
I don't know how to be controlled when you just say, okay, just reshape it.
Yeah, so you can indeed reshape it to actually you're kind of getting ahead of where we're going. Yeah. Once we get a few more skills down, if your question is not answered, then ask it again. So if we just naively reshape this to 4, there's another question, sorry.
Sorry, can you remind me of the convention for qubit counting? Are you going from right to left with 0 to n or?
Okay, let's scroll back up and check together because I feel like if I answer this off the top of my head, I'm gonna, okay, yeah, so we're going from right to left.
So x0 would be x on the rightmost.
Yes, yes, exactly. It's very easy to get this wrong, so I'm like, check every time. Okay, so if I just naively reshape this, and again, kind of a foreshadowing of what the answer is going to be, and just multiply these two matrices and output a vector, you can check this for x on various qubits and compare with the worked answer here. And perhaps not surprisingly, the answer is wrong. And the reason for this is that we reshaped the underlying psi without permuting so that we're not necessarily targeting the correct qubit. And so if we just reshape naively to like 4, 2, we're effectively always targeting the 0th qubit because of the way that the underlying Julia memory layout works. So we need to be careful to reshape to like a 2 by 2 by 2, where the number of 2s is the number of qubits, and then permute so that we're actually targeting the correct qubit when we multiply by the gate and then permute back to make sure we don't completely scramble the state vector. So a less naive version of this is a function I wrote here, apply gate reshaped 2. I probably should have given this a slightly better name, like apply gate reshaped better or something like that. So sorry. But again, here we just reshape psi to n tensor, where each leg of the tensor is of size 2. And then we work out the correct permutation, depending on which gate qubit we're targeting. We permute the dimensions of the reshaped psi. And then this effectively is now just a matrix-matrix multiplication. So we multiply this reshaped permuted psi by the gate, and then make sure to reshape and permute back to the correct format. And if you go through and target the various qubits and check, you see that now with this sort of, I guess, somewhat less naive approach, so if you reshape, permute back, you actually get the correct answer. So this is kind of a lot, and I also have another exercise for us here. So we can take another 5 minutes to think about how would you handle gates like swap that target 2 qubits with this sort of reshaping approach. So how can you, in effect, like change the reshape and permute approach to handle, let's say 2 qubits, which may not be adjacent to one another. So like if I were targeting qubit 0 and 2.
In your function, why do you, in the reshape, why do you use
I've reshaped it and now I want.
Sorry?
like you have I arrow 2 in your shape?
Oh yeah, so this is because this is creating like an n, it's a tuple with n elements. So it's what effectively this is doing is for I in 1 to n qubits, generated tuple using this function. And this is an anonymous function that just maps whatever I comes into 2. Because we know the dimension of each qubit is 2. Sorry, that is kind of confusing if you're not used to n tuples.
This is 2 questions. Now I have x qubit. And now 100.
Expensive. But that's the dimension.
This is
That is this one.
this one. It's gonna be. She explained how to do that.
I think let's just assume that you can.
Sorry.
Oh yeah.
Is there a particular choice of executing the gate from the right on the state vector? I think I saw mostly more commonly the opposite direction.
Yeah, I mean, it's effectively an arbitrary choice I made, partly because I reshaped this so that the second dimension here is 2. This is like, again, for the single qubit gate situation. And then because of that, I want to multiply the gate on the right. There's no real, like, I don't know. There's no like stone tablet that says that ordering is better. It's just an arbitrary one that I picked. But
Permuting such as qubit on which you apply this qubit 0. You apply the gate of then permuted as
Whatever two or maybe we have reshaped somewhere.
yeah.
That's a contract.
Yeah.
And not used to do here, I don't know, they're
actually faster.
and do tensor contractions.
You get to just.
Because it's like
Actually also and eventually perform this matrix multiplication.
It depends on the library. Some of them do something less naive that we're going to discuss. Yeah. Oh, what's going on?
Alright, I mean, I use this
process exit restart.
Yeah, sorry.
for our next tensor. Let's say do X on the right, but you have to make sure
with the vector 0. So then you have a 4 vectors. The 2 is the 0 1, and then you have a matrix of 4
unless you actually have come up with your own
yeah, exactly.
some kind of
Yeah, so that's
something.
that's why this is applying here. Like here.
It's quantum. There are a lot of these. Well, I assume my call the speed increase. So I'm assuming it has to they finish the competition, someone
So as you have the second law, 0 minus 1 0 0.
So like this vector alpha. It's not like
Emily, things are working.
Yes. So this would this code. C
Cool. I love that. I love computers. Quad 4.8 opus could never. Quad 4.8 opus could never.
Then the matrix multiply then that is
Oh, there's a question.
Quick question based on the arithmetic here. In the line phi reshape star equals gate, are you so that thing expands to phi reshaped equals phi reshaped times gate?
Yeah.
Are you assuming that the gate is symmetric or the gate is its own transpose? Because otherwise I think you might have to multiply it by gate transpose to get the arithmetic right.
Yeah, it's possible.
Right, because the unitary is actually U psi.
Yeah.
To get the arithmetic right, you might have to do U transpose.
I think it might be an artifact of me testing this with a gate that is Hermitian.
Yeah. Not just
We can just do
if you try it with Y, you might.
Yeah, exactly. If you try it with Y, you might discover there's an adjoint needed here.
just applying the gate on the qubit is better than applying it on any error. Because we're removing the tensor I.
Is that like when you showed me that thing that was like going from tensor I to just but that's just from how we take the vector.
So let's say you want to apply the exceed on the second qubit, you have to reshape it, and then the second qubit is not first qubit is applied just the exceed.
It saves so much time.
Apparently, that's what I like.
zero.
But then other like this get also. Zero is the one that's.
Sorry,
Yeah.
sorry again. It needs to be transposed.
Yeah, sorry.
It's only the indices of the gate that get changed.
Yeah.
because of this. Sorry about that.
It's on me. We're using literal engineering.
It's going to a strand.
Zero.
Okay.
So.
Is she changing? Oh. All of a sudden, it's rendered again. Cool. Okay. So in the interest of time, again, because this is kind of a long notebook, I'm gonna keep going. So if you want to keep working on your reshaped guy, go for it. So earlier I claimed that the reshaping approach is better than the naive one. So in what circumstances is that true? So there's this nice package called chair marks that's like benchmarks, but it's smaller. Yeah. So we can use the chair marks package to just quickly see like how using the different functions affects the performance. So here I created a just length 8 state vector called size small. In fact, I have a little function here that generates a new one for me each time. This means that we don't count the computational effort of just generating the benchmark case when we actually run the benchmark. And then I create a function called naive runner that just applies it on a certain qubit with x. And the reshaping runner, which uses the reshaping function instead. And chair marks has a nice benchmarking macro called @b. So it's like so small you don't even have to write like @bench or @benchmark or anything like that. So here I can just benchmark with the setup. So just make me a size small and then use the naive runner just to kind of get some sense of how things compare. And similarly, I can make myself a size small. So the setup argument comes right after the macro and then pass it into the reshaped gate applier runner. And so when I did this for like a pretty small, like length 8 state vector, actually the reshaping one is a little bit slower. It's like 200 nanoseconds versus 160 or so, which isn't that surprising. There's some extra internal work Julia has to do just to generate the overlay for the indices. But if we try and run this on something substantially larger, so if I run it on like a 12 qubit state vector, which is actually many, many times bigger. So I created a function here, scibig, to just generate some slightly bigger state vectors. And then we compare, again, the naive case versus the reshaping case. You can see, at least on my laptop, results might vary on yours, that the naive one does substantially worse. So it takes about 73 milliseconds versus 14 microseconds. So the microseconds obviously are also 10 to the 3 smaller. So the performance difference between the reshaping and the naive approach is pretty dramatic for larger systems where 12 qubits isn't even that large. And again, it's not that surprising because I said that, you know, creating all these Kronecker products and doing the matrix vector multiplication is like sort of the most absurdly inefficient thing you could do, but it's still good to check. So part of the reason that there is such a difference is because of all the allocations, but also just because the matrix vector multiplication in the naive case takes up a large amount of time, since roughly it scales as O(n) to the 3. So if we can avoid constructing really large matrices and multiplying them, that would be good. And this is also, yeah, part of the reason the reshaping works better is because the matrix vector multiplication we have to do is much smaller. I guess the other important lesson here, which we also talked about yesterday, is that it's always worth it to benchmark stuff or chair mark it, whichever package you like better. Because the intuitions we might have about which function works best in which case can sometimes be wrong. I mean, in my case, they're usually wrong, but maybe your intuition is better than mine. And It's worth checking this because, again, for smaller systems, the more naive runner can actually be more effective. So there are actually situations, for example, like if you're simulating a quantum circuit, but you have a quantum Fourier transform that's applied only to a subset of the qubits, it can sometimes be substantially more efficient to just construct the full matrix for that and apply it versus applying each gate on its own. So it's almost always worth it to benchmark things. And another quick exercise for those who are interested, I guess we're about halfway through, and how far am I down this notebook? Is we can also try and adjusting the very naive function above for computing the expectation value, but now have it use the reshape, permute, reshape approach. So effectively what you want to do, I have to like scroll up a ways here, actually, sorry about that, is take this function, which was kind of stupid in using all of the Kronecker products, and rewrite it in the same way as this reshape, permute, reshape, but for the expectation values. Okay, I'm just gonna put the exercise up here. I feel like the bottom of the screen is not that visible. And I'm also going to step out and use the washroom.
One step is start in this. Zero qubit. So it's just that. What if I want to apply like a double gate on the 0 qubit and the 5th? Yeah, I'm not really sure how. I have 5 qubits state, but we have 2 qubits here, acting on the first and the third qubit. Yeah, I think, yeah.
Oh, what's up?
I don't know how to do that.
So now if you want to solve, let's say.
Sorry, I'm confused about the question. Yeah.
Oh, you want to do the others?
I mean, if you're using the state vector to simulate the quantum device, right? Like if you're doing VQE or something and you don't.
Are using this logic. It's just gonna skip that address. So just add this one.
I think I don't understand how.
Yes. So let's see. So do you understand the reshape idea? These are do you understand this? Because once you reach yes. If it is like yes. We can go through.
Yeah, exactly.
Now we understand. Yeah, so this is what's happening here. The way we so the size of the 7 has the first 4 by 2 was this is instead of doing side root something like in place 4 by 2. That's the encoding smaller. Yeah, so I don't think it's the expensive, right? It works fine. Yeah, it's just not yeah, exactly. This is doing is isolating the tiny so funny.
I'm also going through and being like, oh, I have a typo there, I have a typo there in my life.
So this is just
Oh, wow.
Just the Gemini is telling me permuted so that you make it diverse to qubits, and then you apply.
So every circuit it starts with some initial.
Just like how you should apply just
this thing and then when you want to print it out, you just session back to where it was.
yeah, and then you
So if you want to apply,
and then you have to do the permutation as well. But you do that after the reshape.
Yeah, that makes sense. Oh, I guess like first yes.
I got the first.
So on the heavy lifting this
yeah.
Full.
Very dense identity.
So size 0. The size of each I mean size 0 and side was switch. So this needs to switch.
Yes.
And 7 and side needs to switch. That's the permutation. When you apply gate, so then you would permute this and then apply.
Nope.
Okay.
So I guess also in this, just keeping stuff moving, it sounds like a lot of people are making progress. So the reshaping and permuting works pretty well for larger size systems, but we can actually do even better. One reason that we can run into problems, especially for larger qubit counts, is that the permutance function itself can require a copy. And if we're a little bit clever and careful about how we use the indices, we can do almost every single operation we need completely in place, which is great. In general, if we can avoid copying stuff as much as possible, especially really large objects, that's good. It also can reduce pressure on the GC, which is helpful. And as a bonus, we can have a little bit more control over how multi-threading is used. So in the reshape and permute and then reshape back approach, there is some benefit you can get, especially for larger gates, from multi-threading, because probably BLAS under the hood is using it. But with the method we're going to start using now, we can have a little bit more control over how this actually works. So this is possible because we're going to exploit the fact that specifically we're dealing with qubits. Oh, and I have another typo there. And we're also maybe vaguely aware that these integers that represent the indices on some classical computer are also represented as bit strings, sort of under the hood. And in fact, we already kind of were dealing with this earlier when we were labeling our coefficient stuff like psi0 and psi3. So we'll take a little bit more of a deep dive into how it is actually that Julia represents integers behind the scenes and how we can exploit this to do this computation much more efficiently. So we have several inbuilt functions that we can use to represent how these integers are actually stored by the computer. So again, this is the result from my system. If you're like on PowerPC or something, like some crazy CPU architecture, the result you get might be different. Hopefully nobody here is on PowerPC. Okay, actually, hold up. Show of hands, who knows what PowerPC is? Okay, perfect. The curse has finally died. This is an old CPU architecture that was like popular on some supercomputers and a source of an insane number of Julia bugs. So if we have these indices 0 to 7, which I picked for probably pretty obvious reasons, we can actually go through and inspect the digits of these represented in base 2, so binary. Here I have this little loop that prints the digits of this index. So it prints the digits of whatever integer it is, and then I pad it out to represent all 3 digits, and I say that the numerical base I want the digits represented in is 2, so that's what these little extra arguments are for. And if I print this, you can see indeed that index 0 is all zeros, and then index 1 is 1, 0, 0, index 2 is 0, 1, 0. If you ever had to sit through like an intro to CS or EC class where you looked at binary representation of integers, this probably looks pretty familiar. So the way, oh, there's a bug on me. The way Julia is representing this has the least significant bit on the left, which is kind of frustrating because that's exactly the opposite convention I picked earlier, mostly just to make myself and others upset. And we can also go through and look at this other function, bitstring. So these integers are actually, the native integer type on my computer is an int64, so it's a 64-bit integer. And bitstring just dumps the full binary representation of my integer. So here I've just called it again for all of these integers. So that's why there's like 64 zeros here, this is kind of a pain in the ass to read, for which I'm sorry. But you can see in the actual just like raw bitstring dump representation, now index 1 has its least significant bit on the far right, which is exactly where we wanted it to be to match up with the convention I picked earlier. So I guess also a sort of important point here is that it's fine to use either of these functions, but it's just worth being aware of which one counts from which end. So here I'm probably going to stick with bitstring just because it matches with the convention for the qubits we picked earlier, but there's really nothing wrong with using digits if you like that better. And again, this ties back into the discussion of endianness at the front of this. So sorry for all the CS majors here. I'm hopefully not going to completely butcher this. So all of the numbers that we're dealing with, like all the integers, floats, whatever, are represented in the computer memory as bytes, which are groups of 8 bits. Then, because this int64 in Julia is composed of 8 of them, and if I had an int32 of 4, I have effectively 64 bits that represent all int64s. So this is also why there's like a maximum size of a 64-bit integer, at which point you roll back over and you pick up a minus sign and everything is horrible. So one way you can manipulate these integers is with this concept of so-called bit shifting. So you can actually shuffle the bits in the integer around, and if you're a little bit careful about it, this allows you to move from one integer to another in a way that's going to be very useful for us. So in Julia, as in a lot of other languages, like C also has these, of course, we have two bit shift operators, shift right and shift left. And we can look at what each of these do. So each of these operators takes an integer and then a number of positions to shift. So if I have this integer from 0 to 7, I first dump its regular bit string and then the result of shifting left and shifting right. So for the all zeros, nothing interesting happens because it's all zeros, so how would you even notice? And then for index 1, where I had a 1 right on the end here, so at the most right position, if I shift left by 1, you can see that the 1 in this bit representation has indeed shifted left by 1. And if I shift right by 1, then it's all zeros. And there's a question.
I've lost maybe the physical meaning of the shifting of bits.
How do you mean?
Like, what is the physical representation? Like, what do we? I kind of shifting bits for like information purposes, perhaps. But then, what is that like real world?
So what this is going to let you do effectively is connect indices that are connected like by a certain gate. It's a much more efficient way of achieving the same effect as the reduce, permute, or reshape, permute, reshape. And it allows you effectively, it's a way of saying there's a connection between these two states in the state vector mediated by whatever operator I'm applying.
That's convenient.
Yeah, it's very convenient. So we have to do a little bit more like accounting, if you like. But the benefit we get is that the performance can be substantially better. So indeed for 2 also, I'm not going to go through all of these just so like you don't have to listen to me read this. But if we shift left by 1, again, we see the 1 moves left by 1. Wow, really exciting. And if we shift right by 1, then it moves right by 1. Okay, great. And if you want to verify for yourself for all the others, you can go through and do that. So we can use this to apply these gates we want to look at much more efficiently, or indeed the expectation values. So let's look again at this like some generic single qubit gate G that operates on qubit 0. We have some matrix representation of G that looks like this. So there's some element little g 0, 0 that maps the incoming qubit 0 to the qubit state 0. And then there's G01 that takes incoming state 0 and maps it to 1. And then similarly for the other two. So we can actually apply G to some state vector in an allocation-free way. If we take our 3-qubit example that we had above, and we looked at earlier, oh my gosh, I don't want to drag this cell. If we reshape it into this 4x2, we could target qubit 0. And we can do the exact same operation, avoiding the reshaping entirely using the bit shifting and in a way that's a bit more generic. So this can be kind of subtle, so I'll try and go through it relatively slowly, and we'll also have some worked examples in a moment. So if we have this 2 to the n state vector, so in this case it's length 8, but it could be basically arbitrary n, we want to connect some states 0 and 1 on qubit 0, which means that there are 2 to the n minus 1 such connections to make. We also saw this in the reshaping above, where we went from 8 by 1 to 4 by 2. So if you look at this list of indices IX from now, so this spans the entire set of indices in the state vector. We could try bit shifting for every single index in the state vector, but if you think about it for a moment, you can see that doing this won't be super effective because we'll actually end up double targeting the qubit that we're interested in. The reason for this is that you'll pick up all the bit strings that contain a 0 on that qubit, but also all the bit strings that contain a 1. So you only want to target half of them, so you can map 0 to 0, and then 0 to 1, and then vice versa. So for a single qubit gate, we would instead... Oh, sorry, there's a question. Sorry?
For indexing.
Yeah?
Using IX.
Yes.
So like it's a number between 0 and, for example, I don't know, between 0 and 7.
Yeah.
How do you do two-letter or two-character indexing work?
Sorry,
Because we're we're using the whole I. Okay,
yes.
No.
Okay. So if we only index through half of the indices for the full state vector, then okay, we have half the indices and we need to find a way to target the qubit that we do want. So again, let's say just as an example that we want to apply a gate that targets qubit 1 on a 3-qubit state vector. If you print all of the bit strings of these integers, so in this case like 0 to 3, I have another typo here. You can see that you'll touch qubits 1 and 0, but not qubit 2. And you can again go through and check that yourself with the bit strings. So instead, what we need to do is we actually need to insert a 0 bit at the appropriate qubit. And we can do that with these two functions here that effectively expand the integer using some bit shifting arithmetic and generates the appropriate indices in the state vector to target that we need to look at. So this function is like kind of subtle if you've not done this before. So we'll actually go through and show what it really does. So we want to take some integer ix that's from this sort of half list of all the indices of the state vector and expand it in an appropriate way so we touch all of the segments for the specific gate we want to only once, so that we avoid applying the gate effectively twice or not at all. So here's my beautiful function, expand int. It takes an index ix and some qubit, and then expands, inserting a 0 at that specific qubit. So how does this actually work in practice? So I'm going to slow down right here because this is like quite subtle and sort of the most important part of this whole thing, I think. So if I want to insert a 0 at qubit 1, if I start with just like the all zeros, nothing has changed. And then if I have the ones, annoyingly also this like didn't fully, it gets wrapped around a little bit, which is really frustrating. So for ix equals 1, nothing happens. I have 1 at the end and 1 at the end. But then for ix equals 2, so right at the end here, you can see we have 1, 0, which represents 2. If I insert a 0 at position 1, then actually the 2 has moved over by 1. So now this would be 4. So 2 is mapped to 4. And then similarly for 3, I go from sort of 1, 1 at the end. And again, sorry, I'm really sorry about the rendering here. I go from 1, 1 to 1, 0, 1, which is 5. And then similarly with the bottom one here, 4, I go from 4 to 6. So effectively all the bits that were at position 1 or to the left of it are bumped over left by 1. So if you're still confused by this, it can be worth just going through this loop and playing around with the specific integers. And you can also play around with the specific position you're expanding at to see what this does. But effectively what it's doing is just inserting a 0 at the appropriate qubit, so then we can apply the gate using that. So have I completely lost everybody? A little bit, yeah. Yeah.
This is like very interesting, you know, like the language is very interesting too. Like moving bits, especially when you think, like I'm old enough to have used a CD, right? And so like when you think about
it's very funny that you think that that's like an old person thing to have done.
Yeah. So when I think about this, I think like this is all post-processing, right? So like my brain immediately goes to like hardware. If you move a bit, you're done. You're done for, right? So this is like, it's pretty cool. But it also means that there's a lot of background memory here too, right? You're like moving whole objects.
Yeah, I mean, what you're effectively just trying to do is find an efficient way of saying like which elements of the state vector are connected by the gate. So this is just like a very low level way of doing that, where you have special knowledge that like, you know, by doing all this bit-based accounting lets you in a more efficient way say, okay, you know, this segment is connected to this segment.
But it feels a bit arbitrary, like you're just moving bits, but these bits are like relative to the things that are around them.
Yeah.
You know what I'm saying? So it feels a bit like you can use them in some instances, but
well, effectively for any state vector simulation with like linear operators, you can do this.
So I mean, it's just like, you know, moving qubits, like if you have some qubit index and you want to know where that qubit is in the state vector.
Yeah, you can think of it like that, or like saying like really just like which input and output states are connected by this object.
Help connecting.
Are we always in the shifting?
Because it seems like if you shift right, you could chop off a one.
Yeah.
This information.
Yeah, so we're in this case, we're always going to shift left because these integers are right endian.
Yeah.
Yeah.
Okay.
But if this were on some crazy CPU where instead like one started here, then you would do everything in the reverse direction. So you would have two migraines instead of one.
So you do permanently lose if you shift it such that the one.
Yeah, it just becomes a zero.
Okay.
Yeah.
So maybe, I don't want to, like, so maybe you could like describe this as a map because you have n qubits, but you have like 2 to the n.
Yeah.
Similarly and classically, so this is kind of a translation between them, right?
Yeah, you can, I mean, again, effectively, all you're trying to do is say like, given a qubit that's applied to qubit Q, give me a list of input states that are not connected to one another. That and then the output states, you're also guaranteed none of them are in the input set. And as a result of this, you also need a way to access like, okay, so I need to, if I have an incoming zero, I need to find a way to access the one that it could be connected to. And you can achieve this just by flipping the qubit or the index that represents the qubit you want from 0 to 1. And this is also kind of a bit shifting operation, but it's a little simpler than the expansion. And here I gave it the exciting name of flip bit, where I'm doing a XOR after I shift the flipper, which is this guy, over. So we saw the XOR operator yesterday. Some people call it XOR, but I call it XOR. So I don't know, pick which one you like. And here's just like a really simple little truth table for it. So it maps 0, 0, 0 to 0, 1, XOR 1 to 0, and then 0 and 1 or 1 and 0 both to 1. So it's called XOR because it's exclusive OR, so it's one or the other, but not both. Is another way to think about it. And again, we can sort of loop through this if you want to and see how this works. So I didn't include the for loop down here, but you could easily do so just to show some input bit strings and then the result after flipping certain bits at certain positions in them. And the final result is that we can have a shifting gate applicator that effectively does the same thing as it has the same result as the reshape, permute, reshape, but in a much more efficient way. So here we have an input vector psi, some gate where I'm now just gonna assume that for now it's a single qubit gate, and some qubit index. And then we have an output vector phi or phi, whatever you want to call it. And this function right here implements the map from psi to phi, applying this gate on qubit, whatever it is, using the shifting approach. So it goes through half of the indices of each of these state vectors. It generates the 0 valued amplitude for each one of them with the expanding function. And then it finds the connected 1 state with the flipper. And that's all the information effectively that we need, where we can get the amplitude on 0 and the amplitude on 1, and then just, in this case, by hand, implement the really small matrix vector multiplication. Oh, there's a question, yeah.
Could you explain the X gate in a 2-qubit system using these bit shifts?
Yeah, there's no whiteboard. Oh, no, there is one, but do we have markers? It would be very nice if we had them. But yeah, so there is one. Okay. But yeah, the X gate, especially here, you can actually just think of the flip bit operator as X. Like that's what X does. It just maps 0 to 1 and 1 to 0, right? With no change of phase or anything like that. So if we were gonna do let's see. Sorry, you're also gonna have to put up the fact that my handwriting is really bad. So X is 1, 1, 0. Okay. So if I had, I'm gonna have to do this by hand. This is gonna be really exciting. So if I have like IX is 1, I'm gonna make the bit string much shorter so I don't have to try and count out like 63 zeros. Let's do it with 4, let's say. Then I have x is 2. X is 3. And well, I'll actually do it for 4. I'm sorry, for 3 qubits, just because I'll like a little.
Just 2 bits.
Sorry, counting out my board today. I also have an off my one there. Sorry about that. There. 5, 6. Okay. So let's say we wanted to apply x. Oh, I forgot 0. Whoops. On qubit 1. Second. So what this function would effectively do is it generates a subset of these. So it would have x is 0, so 0, 0, 0. Probably should have done this.
Can just get those numbers from this.
Sorry?
You can just assume we have the numbers.
Yeah, okay. Well, I wanted to draw some stuff on.
Yeah.
Yes. So then I would insert a 0 bit at this position for each one of these. So this one would again just get mapped to this. This one would get mapped to 1 again. 2 would get mapped to 4. And 3 gets mapped to 5. And then when I apply the flipped version, so sorry, I didn't lay this out in the best way. At 1, then ix at 0 goes to 0, 0, 1, 0. Let's do 1, and 2 goes to 0. So I guess a crucial aspect of the flipper here is that if I flip it 1, these two are connected. So 1 goes to 0, 0 goes to 2, and 2 goes back to 0. So this thing is effectively reversible, which it should be. And then for 3, this goes back to 1. So these two are connected. And you can end up working out the rest of this for yourself. So what this effectively means is that applying these two together would connect states 0 and 2. Sorry, what's up? Oh, someone gave me. Hopefully this is not. This is a board master event. And 1 to 3. And then, yeah, 2 to 4. No, 2 to 4. Sorry, it's 4 to 5. 6 to 7. So this one also effectively, if you like write it out in the qubit language, takes 0, 0, 0, 0, 0 to 0, 1, 0. And this one takes 0, 0, 1 to this. So effectively what's going on is like these bit elements here are just representing the 0 and 1 states in this object. Does that make sense? Sort of? Yeah, there's a question.
Sorry, why did 2 go to 0?
So if I flip this bit right here, so if this is a 0, it becomes a 1.
Oh, you're flipping, not inserting.
Yeah. Like the insertion, sorry. It's really hard to draw this.
Like the first part was insertion, right? Like
Yeah, if I insert here,
that's the result.
yeah.
Okay.
So if I insert at position 1 for ix equals 2, that gets moved down to 5, which is then connected to 4 after I flip.
Oh, okay, so there are like two operations.
Yeah, yeah, exactly. There's insert and then flip.
Oh.
So insert, make sure that you don't like if you don't do if you don't count only half of the indices for 1 qubit gate, you end up double counting, and the problem there is you'll effectively apply the gate twice, which in the case of X just completely negates it. And then once you insert, you have like a unique identifier that can, in combination with the flip, get you for every sort of unique combination of states that's not on the qubit you're applying the gate on. It gets you that unique combo, and then from there you can address the specific subspace that you want to apply the gate on. Which in this case is just 0 and 1. But
so if I think of it like a black box,
yeah,
if I don't fully understand it, it's basically giving me an efficient function which maps a specific set of indices that will be affected by the gate.
Yes.
To the output.
Yeah.
Of that gate.
Yeah.
Okay.
Yeah, exactly. It is confusing. Like if this is the first time you've seen it, it's not obvious. So.
You like the X before like inserting like mapping 2 to 4 and 3 to 5.
No, so you insert before you do anything else. Sorry, I drew this in kind of a funky order. I'm sorry about that.
You do the flip then go?
Sorry?
You do the flip then go to that 6.
So what the flip gives you is it says like, okay, like if I
have a relation, yeah.
Okay.
So if we like don't do this appending or whatever, like shifting, we have those relations. That's 0 and 2 and 1 and 3 are like now if we insert that and we do the bit shifting, then we do a bit flip.
Yeah, so I mean what the flipping is, sorry. You insert to get like let's say like these zeros, and what you want to do then is say, okay, given that this 0 this is 0 on the qubit that I'm interested in applying the gate to, then on the other qubits, it's all 0. Sorry. Stop the insertion, which is different than 1. So 1, except on this qubit, has a different bit structure on the qubit that I'm not applying the gate to. So then, what are the other sort of unique bit strings that can result from applying X to this? And the way you can figure that out is with the bit flip. One of them is just this itself, which is just like, which would be this, of course, is 0. So we don't have to worry about that one. And the other one is the bit string here that is unchanged except for 1 on this qubit where we're applying the gate, which in this case would be this. Sorry, there's another question back there.
Yeah. Is there utility for like the reverse of like this entire operation?
Can you say that a little louder? I'm sorry.
Yeah, of course. Is there utility for like the reverse of the entire operation?
It's not that so much as just the fact that you're saving a huge amount of talking. So for smaller systems, it's not so much of a problem, but like if you're doing a larger state vector simulation where you have something that has like 2 to the 34 elements, which is right at the boundary of what can fit in like most classical computers, then if you have to permute dims, i.e. copy, the simulation is just completely infeasible. So this makes it possible for you to go to larger system sizes, and then for the ones you can access, as we'll see, it makes the computation substantially faster. I mean, since we're doing like unitary gates here, in theory, the whole computation is reversible anyway. You could indeed just reverse with the reshape, permute, reshape anyway. But this thing, despite being really annoying, has some benefits, which is why we're talking about it. Yeah.
So this is from X-gate, which just flips the signs, right?
Yeah.
As far as I know, like if you needed to represent something with a complex amplitude, like this is sort of like a bit shift goes to that. But what if you can you use this technique for complex numbers, or is
yes,
it like okay?
That's exactly what this function in the notebook is showing you.
Okay.
It's just saying like what are the indices like what are the 4 indices that are connected
Mhm.
by this gate on this qubit for each bit string that's not on that qubit. And then for the ones that aren't on this qubit, it's those are completely disconnected from one another, so you can do them all in parallel, for example. And you're guaranteed that you're not going to be like mixing regions. All right, again, I drew this in a very funky way. Yeah.
This is for 1 qubit.
Yes.
For 2 qubit, we get
We'll get there.
set of rules.
We'll get there.
Okay.
That's a later exercise. Okay. So again, what this function is trying to show is that given an input index that spans like only half of the possible indices, from there we can generate the amplitude 0 and amplitude 1 for your like complex number question that are connected by the gate. And then from there we can effectively do like this 2 by 2 multiplied by 2 operation. So here I hand unrolled it because I didn't want to write the multiplication out for whatever reason. And also just to try and make it like a little bit more obvious, I guess, what's going on. So here, this can loop through every single one of this, like half of the full index dimension of the state vector and apply the gate independently in a way that avoids mixing for every single index. Also, I guess the other advantage here is that these bit shifts are in general like very efficient. They're usually a CPU opcode. So usually, I mean, not always, they're very fast. Okay. Other questions? This part is very confusing, so yeah.
So would you mind reiterating why it's half?
Yes, okay. Maybe I'll actually try and do this. Sorry, no, I'm so sorry.
Do you want me to try and then one more time?
No, it's okay. I can do it over here. Okay. So let's again do like we have 3 qubits, which means 8 indices. Okay. So I have 0, which is just 0, 0, 0, 1. Okay. So this is actually these are half. And then okay, so here's all the possible indices I can have for my 8 qubit state vector starting in 0. So for x, if I flip on this qubit, the ultimate result we need is that this is connected to this, like these two are connected. 1 and 3 are connected. Okay. 4 and 6 are connected. And 5 and 7. Good so far? Okay. So what I'm going to argue is that if we only focus on this half and we insert and then flip, we can recover all of these relationships without having to go through the entire thing. So the reason for that is like, I'll try and write this in a little bit, maybe a little bit more coherent order this time. So for 0, this does nothing because it's all zeros anyway. For this one, it also effectively does nothing because this is also a 0. Then this one moves over 1. So this has already become 5. So we already managed to access the bottom half of the index spectrum by only looking at the top. And then this one also, sorry, this should be 0. Okay, so by expanding it 1, we moved over these, and now this one is also down here in this region. And if we look at these indices, each one of them is one that appears in the top in these sort of like bimodal, or sort of these back and forth error relations.
Can you say one more time what year do you need to go from there to there? What
The
is it?
so I'm expanding it 1. So everything to the left of this qubit is shifted left by 1. These ones are untouched. Anything in this column or to the left of it is moved left by 1. So the other thing you can see is that now, once I've expanded it 1, all of these are 0. Okay, people with me so far?
Yeah, and just you're saying like you can recover the bottom portion because of the linearity properties.
Well, you can recover you get the bottom portion because you've expanded basically like all of the, from this half, you can get the bottom ones that only have 0 at the qubit of interest.
Oh,
yeah.
And
I can also just like write what their names are. This is 0, 1, 4, 5. So I guess the other thing to notice here indeed is that for these indices, none of these are connected by an arrow to each other. So you don't risk accidentally applying the gate twice. Okay, so you've expanded it 1. Now from here, you want to generate the indices of all the amplitudes that are connected by X, or it doesn't need to be, it could just be some gate G. So here. G00, G01, G10, G1. So we want to find some way to apply this arbitrary gate G, which I assert is a unitary, okay, in a way that doesn't apply any of these elements twice, so it doesn't go forwards and back. And the way we can do that is once we've expanded it 1, then we can get.
Could you specify why we expanded it 1?
Because we're applying to qubit 1. I'm applying G on qubit 1. So if I were applying it to qubit 2, then I would expand it 2. So I would expand then here.
okay.
And if it were 3, then I would expand up. I would 1 to the left.
Okay.
Yeah.
So where is our targets?
Yeah.
Qubit.
So
Do we
we
just
start
add
with 1, right?
The
Indexing
all
the
zeros, or do we also need to add the all ones?
0, 1.
So we're about to get to the 1s. So once we've expanded to 1, now we need, okay, so this is a single qubit gate, so I need 2 amplitudes here. I actually didn't give myself enough space again. Like psi 0 and psi 1, right?
That's the rightmost.
So we have psi 0. Here's all the zeros. How do we get psi 1? We flip. So this one, if I flip at 1, so this one, do nothing. And then flip at 1. This one then becomes 0, 0, 1, 0. So here now I have a pair of indices that are connected, the 0 and the 1 state. And that's all the information I need to be able to get the amplitude of psi for 0 and for 1 on the reduced subspace of this qubit. And then similarly for here, if I do nothing, I get 0, 0, 0, 1 and 0, 0, 1, 1. Where again, I have this connection between 0 and 1 here. And this also already gives me the 1 index for free, so I can also handle the 1, 1 case right here. And then for this one, again, kind of didn't give myself enough room. 0, 1, 0, 0, and 0, 1, 1, 1. After flipping, then finally for this, I get 0, 1, 0, 1, 0, 1, 1, 1. So this gives me all the pairs that can possibly be connected by this gate on qubit 1 without mixing any of them. Because if you mix, you're going to get the wrong answer. Okay. Good so far?
It's fun.
This is just help.
Yeah.
Just have to.
Would it help if I went through for qubit 2?
I think it's
Maybe just for
using different
completeness.
combinations, so.
Maybe
Different
draw some
gates,
brackets
same
like which
thing,
G
but just
maps
different
between which pairs of
Yeah.
states, just so we can see. the
Yeah,
whole
okay, so
reaction.
then, no, that's good point.
Exactly.
So let's zoom in on this one.
Kind of how you do.
So then the claim is that G
It's gonna be.
on 0, 1, 0, 1 to 0, 1, 0, 1 is G 0, 0. Because that's not from 0 to 0 here, right? And then G on 0, 1, 0, 1, 2, 0, 1, 1, 1 is G 0, 1. And then similarly, G 1, 0. And then if I have all ones, then that's G1, 1. But once I have these two indices, I have all the information I need to look up the two amplitudes I need to actually compute this. And that's indeed what's happening in this function here, where once I look up the amplitudes, and again, I have to add a 1 here because Julia is 1 index, not 0 index. Then I can just apply these gate elements, again, suffering from the fact that Julia uses 1-base indexing to update the amplitudes in the output state vector. Okay. Okay, other questions? Oh, yeah.
No, it's might just be a repetition of what people have asked, but just to sort of get the general picture here. So that this whole thing was an efficient way of getting the indices of the amplitudes that you wanted to apply the gate to.
Yes.
So for small systems, doesn't really matter, but if you have a huge system, then you can.
Yes.
Okay, that makes sense.
Yeah,
Okay.
it doesn't even have to be huge. I
Okay.
mean, we'll see that you can still benefit for relatively small systems.
Okay. Thanks.
Because you no longer have to copy. This is all in place. And you can do all of this in parallel, right? You have here, like, these 4 are all handled completely independently. So you could run all 4 of them in parallel. Okay. So here I had some, I guess, like just quick examples, just testing out that this works correctly compared with the naive function. This is the other advantage of having the naive function, is that it's like kind of dumb, but it lets you check quickly whether the answer you got actually makes any sense. And here I just created an unnecessary copy of the output state for the convenience of testing, but in fact, you need not do this. You can do everything completely in place in a safe way. And it means that you don't double touch any indices and apply any gate elements twice. So if I write this in a way that doesn't involve any copying at all, so the only change here is I now just directly write the output amplitudes back into the input state vector. Then you can benchmark this for relatively small systems and relatively big ones. So already we can see even for the small system, which is like 8 qubits, this is an order of magnitude faster. So instead of like 100 nanoseconds, even compared to the naive one, it's now 16. And for a larger system, where we, like, I think this was 12, it's again, like about 10 microseconds faster, partly because there's just more indices you have to go through. But for a system of like 30 qubits, the performance benefit is really substantial. And we haven't even started using parallelism yet. Okay. So if we keep running this, we can then also start doing stuff like using multi-threading. So since all of these operations are independent of one another, it's a really good use case for like naive threading. So in this case, I'll just try and multi-thread sort of this internal chunk, since all of these IXs are completely independent of one another. So how many threads I have available is going to really depend on my machine. In my case, I apparently have 4. I think I might have restricted this when I started running the notebook, but in any case, 4 is enough to see maybe some benefit. We'll see. So when I run a version of this that's now threaded, I can see, I should have maybe set this up slightly differently. So for the big case with the threading, we see that actually it's like kind of comparable to the non-threaded case, but it's still better than the reshaped one. So part of the reason for this is that even like my quote unquote big case is actually relatively small. It's only 2 to the 12 elements, which in this case, like the actual amount of parallelization is only 2 to the 11 because we're cutting the entire index range in half. And that's probably not big enough considering all of these tasks are small. So there's some overhead from the Julia scheduler of like creating all of the tasks and managing all the threads and checking like, hey, are you done? Can I give you more work to do? So this is another reason that it's probably worth it to benchmark. So in this case, for this, I guess like I kind of screwed myself over by calling it a big state vector. It's more like medium sized or like we ran into, is it grande at Starbucks for the medium? Okay, venti is the big one, right? All right, cool. Yeah, this is like a grande size state vector. It's not even venti because it doesn't have 20 qubits in it. So Julia by default uses this so-called dynamic threading. So as one thread finishes a chunk of work here, the scheduler says, okay, here's a new piece of work for you. So that can have a lot of advantages. For example, if the tasks you're running can take different amounts of time, or if you're not sure how many tasks you're going to have. In this case, something like static threading, where when the loop is instantiated, each thread is given a specified amount of work to do, might work better. That would also be something to look at. One advantage of using the dynamic threading, and this is, I think, something that's really nice about Julia, is that you can nest threaded loops. So you could have an outer loop that's threaded and then an inner one that's also threaded. If, for example, you were trying to simulate multiple state vectors at once, so if you were doing some sort of ensemble calculation and you had like 200 state vectors, you could thread both the outer computation and then in the internal gate applications, and the scheduler will just start sending the pieces of work to threads as they become available. This recently got much better in the scheduler, so I used to advise people being very careful about doing this, but now you can be slightly less careful. But at the end of the day, the only real answer to when you should or should not do this is just to test it with benchmarking. The other thing you can try doing, there's like a little example here, is chunking the work yourself out by hand. So you can say, okay, I know that I have to do like 2 to the 11 gate applications here, and I'm going to try and chunk this into blocks of 2 to the 8. So this function here implements for this for us. It effectively just splits the main for loop into 2 separate ones. One that is threaded and one that isn't. In fact, secretly under the hood, the scheduler already kind of does this when it knows that your loop is of finite size. But okay, we can still try it and see if there's any benefit. And in this case, in fact, there is not, mostly because there's some additional overhead of me setting all this up. But this is just an example of another thing that can make sense to try. It makes probably a little bit more sense in situations where you don't have sort of inner segments of the loop that all take the same amount of time. Okay. And if we try an even bigger, here's my venti state vector, the 2 to the 20 one. So this is a 20 qubit state vector. Then even with this one, we see our by hand approach of chunking isn't doing very much for us because the Julia scheduler is now really good. And generally, if you just give it some big threaded loop like this, it can handle it pretty efficiently. And even in the case where we have several state vectors that we're trying to simulate, the Julia scheduler is actually now still really good. So I guess the takeaway here is that this like sort of technique with bit shifting can be very effective, especially if you use the threads, but you don't need to spend too much time worrying about the specific thread allocation because the scheduler is now good enough. You probably are not going to defeat it in terms of how much time it takes to do anything. The other, I guess, lesson here is that it's often worth actually benchmarking stuff to confirm whether our intuition is right. So, or in this case, chair marking. So having done that, okay, great. And now we can start applying a couple more optimizations. So I guess I'm going to contradict something that we talked about yesterday, which is that like you should never use at inbounds. So we can just try it and see what the result is. So in this case, this is the same single qubit bit shifting application as before. It's just now we say for every single one of these array lookups, of which there are many, everything is in bounds. So this requires us to implement the bit shifting like more or less reasonably. But if we're pretty confident that we did so correctly, then we can turn off all the bounds checking and see if there's any benefit. And the short story is from the small chair marks I ran that in fact there isn't, because again, the Julia compiler now got good and it can recognize that there's not really a huge benefit to doing this. Okay. So you'll sometimes see, I guess Julia's been around long enough, like if you Google like some Julia performance tips, you'll still see like sort of phantom answers from like, or zombie answers from like 10 years ago that are like, you should always use add inbounds. But this is just another example of, in sort of today's Julia, it doesn't really help you that much. And without it, you run the risk of just getting horrific site faults everywhere. Okay. So with that done, we can say like, okay, I'm still not happy with the performance of this. I think, 500 microseconds is still too long for this 20 qubit state vector. I want fewer microseconds. So the next technique we can try is actually just using the profiler. We applied some pretty obvious optimizations, some less obvious ones with the bit shifting, and now we can see if there's anything else we can do to improve the performance. So Julia has another standard library that allows us to pull in its profiler. And this didn't profile for me. Hey. Let's see if this runs again. It doesn't want to run. Oh no. Okay, let me see if I can do like
If you put the thing in a loop.
Yeah, exactly. That's what I was about to do. Last time I ran this, it was slow enough that it actually it actually ran slowly enough. I'm just gonna like run this like 200 times. Let's see. There we go. Now I got some stuff. Yeah, so when we start running this, we're just going to clear all profiling data just in case there was any that was accumulated. Then I instantiate just some 20 qubit state vector and try running the gate on it many times and then print the result. This is like kind of hard to read, so I'm sorry about that. But it looks like we're actually spending a lot of time in these various threads, which is kind of annoying. And then somewhere down here, I'll see if I can find it. Last time, at least I looked at this, I'm not going to like try and force everyone to look at these horrible colors. This ended up actually spending a lot of time in float promotion. And the reason for this is that I'm testing it with my X gate, which I at the top very naively defined as having floating, like real float elements, but the elements of my state vector are complex. And I think this might have actually been fixed in 1.12, which is maybe why the result is not as dramatic. Oh yeah, I can. Yeah, and the inbounds runner, that's a good thought. Is it in there? No. Okay, well, you'll have to believe me that last time I profiled this, it's spending a bunch of time promoting the elements of gate, which are real floats, when it gets multiplied by this complex number here, even though we know that in fact, we can just represent X equally well as having some complex elements, which are secretly real. I think they maybe finally wrote also like a fallback multiplier that's slightly faster, but anyway. Here we can also force in this slightly newer bit shifting function. We now force that the state vector and the matrices have the same element type. So this means we can call some very fast, low-lying function just for this complex multiplication that should hopefully get us a little bit more performance benefit. And indeed, the short story here is after converting X to be entirely complex numbers and running it with this newer function that ensures everything is complex, we do gain about like 50 microseconds, which doesn't sound like a huge amount, but if you're applying like 20,000 gates, it adds up. So once you kind of have like a reasonable approach for implementing the inner loop, i.e. the bit shifting, then you can drive yourself completely insane doing micro optimizations, like making sure the element type of the gate is the correct thing. And again, my profiling didn't load, which is really frustrating. So rather than forcing everyone again to look at like profiles that aren't that illustrative, because I think also Pluto changed how they rendered these, which is really annoying. There's some more micro optimizations we can do. For example, we can say, okay, if I look at the gate indices above, I can index them as a matrix, so like with 1, 1, 1, 2, 2, 1, or I can say, well, this is just secretly under the hood. This is represented in memory with linear indices, and I know how to compute those, so I'll help Julia out a little bit and write this in terms of just the linear index of this gate object here, which again, secretly under the hood is really a vector just with some indexing sugar on top. And if I run this, it's also a little bit faster. Okay, so then somebody asked earlier about how to implement multi-qubit gates. So indeed, we can do the same sort of bit shifting technique for gates that operate on multiple qubits. And this also can be a really big benefit because we save ourselves a lot of time. For example, if the qubits are widely separated, like in the state representation, we can save ourselves a lot of time permuting. So here is kind of like, I guess, like the last part of this section. And then when we come back in the afternoon, we'll keep going a little bit. But the final challenge of the morning section is to try and write a kernel for the bit shifting approach that can handle multi-qubit gates. So in this case, you don't need to worry about like 3 or 4. 2 is enough. Despite, I guess, what people pretend, almost everybody's just running singular 2-qubit gates. So the goal is to take something like this and generalize it a little bit so it can take 2-qubit inputs and implement this same procedure for 2-qubit targets instead of just 1. So one thing that is probably going to be pretty important here, and which there's a large hint for, is that the order in which you expand is really important. The flipping order is not so much of a problem, but the order in which you expand can end up changing things quite a bit, so be careful about that. And then there's also some more tips and tricks down here. Or if you're like, dang, this is awful and I hate this, I never want to deal with this again, you can also go to lunch early. So we have about 40 minutes left in the morning session. And if you want, just like go crazy, start trying to write your 2-qubit kernel, and we can come around and answer any questions.